This is what we call property testing when we're looking at properties of the code. And if we think back to things like our sorted, our bubble sort in comparison to our sorted had a property that its output is exactly the same thing as a sorting. It also has another property. If, for example, you sort something and then you sort it again, if you call it twice, it's idempotent. It won't change. That's maybe not the case here, but this code should have a property that looks like this. If we reverse the order of the arguments, it shouldn't make a difference. There's nothing critical let's fix this here as well. There's nothing that is important about x or y such that one of them has to be x and one of them has to be y. And you can see here we have our statistics. You can see how many times it had to actually draw, how many examples it has, 78 passing examples, and everything worked. We could also say, I know one detail of one of these values, not necessarily from how the code works, but from details of what the code is supposed to do. For example, I know if one of these values is 0, I know this code's not supposed to do anything. Similarly, I know if these values have some relationship between them, the code is supposed to do something, and it's always supposed to do something here. Here we can see this is an additive identity, and here we have an additive inverse. And as we continue this, we could say, well, I could look at differential cases. I could say, you know what? If I call this thing on f of x and y, and I call this thing on f of x plus 1 and y plus 1, well, the addition of 1 to each of the arguments should, as its consequence, either increment this by that value, or at minimum, it should be strictly less than. Maybe we don't know specifically how this operates, but we know that if we increase each of the inputs, well, the output should increase. And you can see here again, this is a property of the code. It is not just recapitulating what the code does. If we go to something like our Fibonacci implementation. And so remember, in our Fibonacci implementation, we are going to yield an infinite sequence of Fibonacci values. Now note that as a consequence of just absolute pure judgment, we may say there's a certain reasonability to what we can test here. This Fibonacci series is genuinely infinite. We cannot test infinite values in a finite amount of time. So what we might say, fixating on just what we think is reasonable, we're always only ever going to look at the first 10,000 values. We don't think that there's anything meaningful that'll show up after the first 10,000 values that won't be visible in the first 10,000 values. And so we may generate randomly the kernel, the seeds of this Fibonacci using hypothesis. Let's pull in given, and let's pull in a strategy. And the strategy will be a strategy operating on integers for those. So here, A is pulled from the integers, and B is pulled from the integers. And we'll grab the first 10 values from this. And then how do we test this without actually knowing how this works? Well, it's a Fibonacci function. Fibonacci is an integer sequence. Fibonacci sequence has a property. We can just test the property of that. So we can use one of our favorite friends, NYs, and we could look at, let's zip together the islice of gi none for ig in enumerating tgn. Well, we could use NYs to look at windows of a particular size, specifically of size 3. And we could say, take this output, the first, say, 10,000 values, get windows of size 3, where you have A, B, and C in this, and assert that A plus B equals C. That's the Fibonacci property, is it not? That each value is related to the following values. If we wanted to be a little bit looser, we could say A plus B is less than C if we thought maybe we can't exactly fixate on this being the sum of these. We could also look at other properties. We know that this thing converges to the golden mean, so we could even do something like, say, take the first 10,000 values or the first 100,000 values, whatever we have budget in order to test. But we do that, and we could say, take these values in pairs, take the pairs of those pairs, and this gives us AB and CD. And we could say, if this thing actually converges to the golden mean, that is to say, if the ratio of subsequent values converges to the golden mean, then the distance from phi to this value, and here let's get the absolute distance, should be less than the absolute distance of phi to this value. I believe it's like this. Yeah. And we could assert something like that. Or maybe if it hits a steady state at some point, we could observe that they're equal. Note, neither of these tests presume that I have a parallel implementation. I'm merely looking at properties of this code and asserting that those properties exist. Here is the good news. Because the bad news is, well, we need to write our code in a way that we can expose properties. This is one reason why I really like generators and generator coroutines, because they're very small building blocks that reveal incredibly clear properties about themselves. This is also why I really like superficializing anything that works with input and output, because a lot of input and output code doesn't really reveal good properties about itself. And as a consequence, that input and output code, well, if I put it at the superficial most level, then I probably will just handle this with an integration test, and most of my unit testing will be at the core level, things which do have properties behind them. The bad news is we have to figure out what those properties are. The good news is, if we do this the right way, writing property tests is actually more interesting than writing our standard types of tests. They really require that we understand what our code does, and we understand and document and expose important details. Because if we go back to our simplest version of this test, even with the working code of x plus y like this, and we think about the properties that we might be able to expose on something like this, here we'll grab our two imports, we will discover that there's something interesting lurking behind the scenes. Here, I'll write just a couple of simple tests. I'll do this on 3 values, and I'll assert that we have a property that looks like this. And here, I'll do x like that. So we'll assert a property of associativity in addition to our property of commutativity. That is to say, if we move the arguments around or rearrange these in some fashion, it shouldn't make a difference. With just these 2 tests, which really required that I think a little bit about how this works, and hypothesis, I can discover something very interesting, which is, if I run this test on integers, everything passes. But if I run this test on floating point numbers, everything fails. Because I have forgotten that floating point arithmetic is neither associative nor commutative. You cannot say x plus y equals y plus x if they're floating point values. And one of the nice things about this property testing is we may often discover properties that we didn't anticipate occurring in our code. You may have looked at this x plus y and said, that's the simplest thing in the world. Looked at those tests and say, okay, of course, they're obvious. And failed to realize that this code is maybe not specified to work under floats if these are 2 criteria that we really care about. This code needs to have some additional documentation or some additional information provided to somebody if they anticipate that it works equally well on floating point values as it does on integers. There are some details lurking behind this code that we might have easily overlooked, that our tests will give us some return on the investment of the time that we put into them by making us aware, hold on a second, did you consider this very important detail about floating point math?